Now, compared to the other technologies, let's just talk a little bit about what is GaN and why is it becoming an important technology?
GaN itself is a wide bandgap material, and so how it's made, it has a base layer that's silicon, then it has buffer layer, and then the GaN device is grown on top of it. GaN devices are all lateral devices, so there's no like vertical current flow, and so this gives different, say, properties and switching and so on. So in theory, a GaN device so a GaN power transistor can switch at the speed of 200 volts per nanosecond.
Oh, blimey, that's quite...
That's like 10 times more than the silicon one.
That's a lot.
In practice, we will settle around like 100 volts per nanosecond, so half of it. So that gives lots of advantages when it comes to switching losses, but also challenging aspects in EMI.
Of course, because you've got such fast switching, that's going to have massive emissions across a lot of. Yeah, that does actually make sense. At high powers, big emissions, sharp drops. But in terms of the technology itself, if I remember correctly, it's originated from, would you say, from the sort of the RF field of electronics?
Yes, kind of. I mean, the first, let's say, high-ish voltage GaN devices were GaN on silicon carbide.
That's interesting. GaN on silicon carbide.
Yes, and that's down to the fact that the lattice structure matches quite good, and this was actually the research topic of University of California, I think, so 20-ish years ago, and this is where kind of the GaN interest started in the scientific community. And then they kind of moved forward and they figured out, well, silicon carbide is maybe not the best base material because it's expensive. And then they moved on to search for different materials. I think from a lattice match point of view, I think sapphire is also quite good, but also not cheap material.
And what we're talking about there is the fact that different crystals have different structures in terms of like the arrangement of their atoms, and you want them to kind of like be similar so that they bond well. Is that what?
So the thing is, you always need a buffer layer, and the better they match, the less thickness the buffer layer can have, and the less stress.
And that makes sense. So if they were almost identical, then when it comes to growing that layer, it's not going to be like it can align itself essentially to that layer, and it's going to like grow without any defects and sort of warping or stresses in the planes. Okay, that actually makes sense. That's interesting.